Hello everyone, and welcome to the second episode of the Z80 assembly programming for the ZX Spectrum. This time it's come faster than another 4 years, yeah? So in this part we're going to talk about the Z80 registers and the math operations it can do, also about stack and interrupts. And also I'd like to walk you through the code of the ZX Gate visual novel engine, which won the first prize in the WOUD compo at DI HALT 2017 and was used to port the Steins Gate 8-bit novel onto the ZX Spectrum. So let's start off with registers. The Z80 has 22 registers in total. 8 of them are grouped into pairs. Those are mostly used for the math. However, HL is usually used for addressing as well. The other 8 are spares for the same ones in order to perform multiple operations at a time or some other kinds of tasks. You can exchange those using the command exa and exx. Then there are 2 index registers which fit a word, that is 16 bits. They are often used for working with two-dimensional arrays. The SP register contains an address that points to the current top of the stack. I'll talk about the stack itself a bit later. The I register contains the current interrupt address. The refresh counter is used for refreshing the dynamic RAM of the ZX Spectrum, and the program counter contains the address of the currently executed command in the program you're running. And you'll need to do something with those registers, so here are some of the most common operations. First one is add. It can add a register and a constant if the register is 8-bit, or it can add 2 registers. There's something similar to it called an increment. It adds just 1 to a register. The next one is sub. It subtracts the same things that add can add. SBC is a variety of sub that takes the carry flag into account. Well, let's talk about the flags soon. CP is also a variety of subtract that subtracts from the accumulator without actually changing it, and by checking the flags afterwards you can tell what is the number that you are trying to compare in relation to the accumulator. And a decrement is a command to subtract 1 from a register. The F register contains flags and is updated on every arithmetical operation. If the result is negative, the sign bit is set. If the result is 0, the 0 bit is set. The just bit is set if the operation triggered the use of the carry bit. The parity or overflow bit is set depending on the result parity of the operation overflows the register or register pair it was done in. The add and subtract value is used for binary coded decimals mostly, and we'll look into that in a later video. And carry is basically an extra bit to the right for all operations. It's used if the result doesn't fit into 8 bits. So let's move on to the interrupts. You might not realize that, but even when the computer is running your program, it stops every now and then to redraw the screen, check the keyboard, and do a lot of more useful stuff in the background. So those pictures will help explain. Basically, when the processor receives an interrupt request, it has to pause the currently running program and send an acknowledge pulse. Then it switches over to a subprogram called an interrupt service routine, or an ISR for short. And once it's done with the ISR, it just continues with your program where it left off. The interrupt vector on the Z80 is taken off the data bus, and on the ZX Spectrum it's always 255. The most significant bit of the ISR address pointer is taken off the I register. So basically, the pointer to the code to be executed must be located at an address of I times 256 plus 255. However, the ZX Spectrum was widely cloned and rebuilt, so not all computers might be working fine with that concept. So here's a slightly dirty hack to keep it working by all means. First, we write FF hexadecimal 256 times into the RAM at address I times 256. Then we write the byte for the gr command into the RAM, that is 24. When the ISR is executed, the CPU will read the gr command. Then the program counter overflows and resets to 0, and 0 is the very beginning of the ROM, and there is F3H written in there. So what will be executed is relative jump to FFF3 hexadecimal. Then at FFF3 place a GP instruction, which is 195 when compiled, and right after it place the address of your RSR. And after all that, send the interrupt mode to the second mode, and you should be rolling fine. While using jumps and interrupts, you're going to use the stack because you need to store your processor state somewhere. The stack is a special area designed for temporary storage of the data, and it's also the fastest way of memory access. We'll look into that in a later video. The current address of the top of the stack is stored into the SP register. The stack works in the principle of first in, last out. There are two commands to work with the stack. The first one, push, sends the value of register pair to the stack. And then another one, pop, takes the topmost value on the stack and puts it into the register pair that you've specified. Consider this program, and let's look into it step by step. The first instruction will load 10 hexadecimal into the accumulator. Then we push the accumulator and the flags to the stack. It now resides as the first item on the stack and won't go anywhere, hopefully. Then load all 5 hexadecimal into the accumulator and push it again. So now we have 2 items on the stack. Then load 2 hexadecimal into the accumulator and take the topmost item of the stack and put it into BC. That's called pop BC. That means we took the topmost values of the stack and placed it into the BC register pair, as you can see. Then the command add B adds the value of the B register to the accumulator, and the result remains in the accumulator. Then we pop BC again and add it to the accumulator again. The result is the addition of 3 numbers, 10, 5 and 2 hexadecimal, which is 17 hexadecimal. Note how we constantly used the accumulator to store the values, but didn't lose any of them, because we transferred them over to B via the stack. Okay, so the stack is also used during subprogram calls and jumps. And calls and jumps are extremely useful because you'd rather write a part of the code once and then reuse it over and over again than copy it a whooping lot of times. There are 4 instructions that are used for that mostly. Call is an instruction for calling a subprogram. It puts the calling program onto the stack, then sets the program counter to whatever you requested, and continues from there. JP, however, doesn't put the program counter onto the stack and just jumps where you tell it to, without doing anything special. JR does a relative jump, that is either plus or minus 128 bytes into the program. It takes up 1 less byte in the RAM inside your program, but it's slightly slower than JP. It takes 70 states to complete when condition not met, or 12 when the condition is met. And ret, meaning return, is a common counterpart to call. It receives the program counter back from the stack and goes on from where it was pointing to. Also, a word on 128K memory paging. On the Spectrum 128, the memory is split in so-called banks, so the address space is pretty much the same as on the 48K, but you can switch those banks using special commands in order to use more memory. What's so special about banks 5 and 7 is that they can be switched into the screen area and the lower memory area after COOO. That means you can switch the screen to bank 5 and have it display something while you are doing your drawing in the bank 7. And when you are done drawing, you just swap them around and the user doesn't notice you've been drawing something. It seems like a real-time animation to them. They just don't notice it because you are drawing in the background. The control of the memory banks is done via the port 7FFD. The first 3 bits control which bank is selected in the space between COOO and the end of the address space. The third bit sets whether the bank 5 or bank 7 is displayed on the screen. The fourth bit selects which ROM is currently active, either the basic 48 or basic 128. The fifth bit, when set, locks the computer down to 48K mode, restricting all means of memory bank switching, basically turning your 128 spectrum into a 48K spectrum until the computer is reset. So this sample code would first disable interrupts, the DI command, then ask the port 7FFD to switch to bank 1 in the end of the memory. Writing to ports is done using the out command. And since we started talking about ports, it's also worth to mention the FE port. When read, the FE port returns the keyboard state and the tape input state. The keyboard keys are read depending on what exact port you are reading and are split into semi-rows. That makes it a bit difficult because on your average IBM PC or whatever you would get the character code of what user has pressed, and in here you have to figure it out yourself. And when written, the FE port allows to control the border color and enable the tape input called the mic port and change the beeper output. It's not some frequency control, you just have to flip it on and off with the frequency you want to get the sound you want. It's nothing pretty much advanced. It's just directly connect to the speaker. So now let's go ahead and walk through the code of the ZX Gate Visual Novel Engine. So the first file to be compiled is called buildme.asm, and it has a definition for the device as we've seen in the previous lesson. Then it has a define for use pages for music. Removing that line would remove some code from the assembly. We'll see it a bit later. Then it sets the output file, the output base address, and includes main.asm, which contains all the code for the engine. The main.asm is the code to be compiled, and you see the ifdef directive means if this is defined in the compiler using the define directive, then this code will be put in here. However, if we remove this, then it will basically be like this code is gone. That's very convenient if you need to support multiple versions of computers with just one kind of source code. So, when the program starts, as we've seen already, this switches over the lower bank to bank 1. Because we are going to be using bank 1 for this scenario and all that kind of stuff, because in bank 0 we have already loaded the music player code using our program in BASIC. Then it calls to custom characters, which is defined in the font.asm file. Let's look into it. So in here we see some bytes defined, which are basically bitmaps for the characters I'm using in this engine. The ZX Spectrum ROM has support for the ZX Spectrum port, the ZX Spectrum ROM has support for some user-defined characters. So we are starting at 65368, that's the location of the A character in the custom character area, and we load HL with the address of our first character. Then we load BC 11 by 8, and then we run the LDIR command, which means load from HL to DE, and then increment both of those, decrement BC, and if it's not 0 yet, then continue. Otherwise, continue down here. That's a very useful command for sending data over in the memory. So this basically copies all of this into that address. That's very simple, just 4 lines of code to copy all this into the memory area we want. Very simple, right? Okay. So next we have some include files, that font file, disk and whatever, also all sort of kind of stuff, in order not to write everything in a single file. Oh, sorry, I forgot about those. So next call is to sg read sysflags, which basically reads the system-wide flags for the game. I'll look into that a bit later when we are going to look into the disk driver. And then goes jp sg run from start, which calls to the script interpreter to start running the main script. Below all those includes, there's the system variable area, which is used for the engine's current state. We have the variable for the start script name, which is basically the script to be run every time you hit the game over. The script offset stores the current position to the memory, basically like program counter, but for our script, for our game script. BGM on is basically a flag that means that we had music playing before we started loading something off the disk, and BGM name is a variable for the music file name. Then this label start game data and this label end game data will contain those 255 bytes. That is to fit the whole save file into one sector of a floppy, which in TR-DOS, one sector of a floppy is 255 bytes. The save file contains the script name, that is the script we are currently playing in, the graph name, which is the image file that was currently displayed on the screen, the temp flags byte. It's reset on every scene change, but we want to continue playing where we left off, so we save those into the save file. And the other 235 bytes are defined as zeros by default, and those are game flags. Then outside of the save file is the system flag area, which is read from the floppy with the call you've seen above. We'll look into that a bit later. Then there is 5000 bytes allocated for the decompression buffer using the ZX7 algorithm. I'm not going to cover this in this episode because that compression algorithm is basically a plug and play. You just stick it into your code and it works. And then there's the label for the system script location in the memory and the label for the main script location in the memory. I'll leave the link down in the description so that you can read more on the documentation on this engine and get to know what scripts are and what's the system script, what's the main script, what's the difference, and all that kind of stuff. Okay, so let's move on to the disk procedures. They're basically all the same, just the name file differs, so I'll just cover one of them that saves the game. In order to have a clean procedure, first we save all the processor state into the stack, because we might ruin something of this in our work, so we don't want the program to have to figure out what we could have ruined, what could have been done wrong. So we'll just save this for later, then call the procedure to pause the music, call the ROM procedure to clear the lower screen, and display two characters in there. That's a floppy character and joystick character, meaning the game is being saved. And then we call the procedure to reset the bottom text color. We'll see that in a later file. Then we use the FE port to set the border color to 0 and call to the ROM address of TR-DOS. This is to initialize the TR-DOS variables to work with floppies. Then we reset the beta disk interface using the function 0 with the argument 0 of the TR-DOS primary function. That's located at 3D13, as you can see here. Yep. Then we set the border color to 1. That is, as far as I know, that is blue. I can't remember exactly. Then we call the function number 1 of the TR-DOS with the argument 0. That means select drive A, and set the border color to 2, just to have an idea of what's happening in our save procedure. Then we call the 18 hexadecimal procedure of the TR-DOS main function. That means configure to use this floppy. Then into HL we load this address pointer. This address pointer, which contains the file name for the save file. And we set that file name to be the file we're working on. Then we change the border color again and call the function 12 hexadecimal to delete the file if we have it already. Then set the border color again and then set the file name again, just in case it was reset for some reason. Then in HL we load the position where the game data starts. We've seen this right here. And in DE we load the amount of bytes that we want to save. That is end game data minus start game data, meaning all of this is the amount of bytes that we want to save. Then we call the OB hexadecimal function, that is save file. Then we reset the border color, call the function to restart the background music if it was playing, and restore all the values from the stack, so the program doesn't even notice we were doing something. So that's pretty straightforward, right? And all those functions are basically just differ by the file names, but mostly they are all the same. The routines to pause the music are located in the bgm.asm file. This is a file handling everything music related. So you see, the first function in here is a stop BGM, and there's a pointer pause BGM to commands below. The pause BGM command disables interrupts, loads 63, which is the default interrupt pointer for the ZX Spectrum ROM, back into the interrupt register, then sets interrupt mode to 1, which is the default for the ZX Spectrum ROM once again. If we are using pages for music, then it switches to the music page, which is bank 0, and calls the player +8, which is the mute function in the Vortex Tracker player. Then, if we are using pages, it switches back to the first bank, enables interrupts and returns. So if we call to pause BGM, only this is executed. However, if we call to stop BGM, it also zeroes out the accumulator, because A and exclusive OR A, basically with the same number, it always leads to zeros, and it's the fastest way of clearing the accumulator. And loads the BGM on flag, which was right in here, with a 0, meaning that we stopped the music and we don't need to restart it. And the next procedure is restart BGM. It also saves everything to the stack because we might need it. So just as not to have the main program figure out if we change anything or so, it's better idea to save all the registers before doing anything. It loads the value of BGM on into the register and checks if it's 1. Then there's a conditional jump. Z means 0. So let's see. If we have 0 in BGM on, 0 is loaded into the accumulator. Then CP1 basically subtracts 1 from the 0, and the result is -1, which is definitely not 0, so that means it's not equal and the jump is not done. We are restoring everything from the stack and returning where we were. However, if we have 1 in the accumulator after this, then CP1 results in a 0, because 1 minus 1 is 0. So the 0 flag will be set and we'll be jumping right here to the do restart. We'll cover this just in a moment. However, if we call start BGM, we're going to do the same thing to save everything, then switch to the player page, call the player to initialize it, and switch back to our main page for the moment. And here's the do restart label, which is basically the code to set our interrupt to the music routine, as we don't want to overly complicate the engine to have music in background. Let's just leave it to the processor. It still will interrupt every now and then to do something, so why not tell it to play our music instead of doing whatever it's trying to do. So we disable the interrupts so as we don't get hit by anything while we're working. Then we load 24 into the accumulator and place it at address 65,535, which is JR, and which is placed at the very end of the RAM. Then we place JP at address 65,524, and we place the address of our interrupt service routine, which is down here, right after the JP. Remember, that's the old trick I described to you earlier. Then we basically fill the table with FF, as I said earlier about this dirty hack to make it work on all kinds of different clones. Disable interrupts just in case, because LDIR, as far as I know, re-enables them, so I have to disable them once again. Load the interrupt pointer with the current value of the accumulator, which is the first item in our table. Set the interrupt mode to 2, which IM stands for interrupt mode, and 2 is the mode we're going to use. And then set the BGM on flag to 1, meaning we have the music playing. Enable interrupts and restore everything off the stack. So that's how we set an interrupt to play the music. And here's our music interrupt service routine. What's it doing is basically disable interrupts, so that if our ISR takes too long, we don't get hit by a second interrupt while we are servicing the first one, because that would lead to an infinite loop and the processor will get stuck, the program hangs, and the world ends, just something like that. Then we place everything onto the stack again, then switch over to the spare registers or the shadow registers, because who knows what the player could be doing, and push everything again onto the stack. So now we have the main registers and the spare registers, all of them on the stack. Switch to the musical page, that's bank 0, call the player +5, which is, according to the Vortex Tracker documentation, is the routine to be called every interrupt to play the music. Disable interrupts once again in case the player re-enabled them, and switch back to bank 1, where is all of our code, scripts, all that kind of stuff resides. Then put back all the alternative registers we've had saved, switch over to main registers once again, and put back the main registers we've saved, enable interrupts, and we are done with it. So that's a very short interrupt service routine. Basically, you could have thought that you can just call the player routine, but the player routines are usually very dirty in terms of stack and flags and registers, so it's better to be safe than sorry with all those stack saving routines. Yeah, And down below we have the addresses defined, which is C000, the start of the bottom bank, where we have our Vortex Tracker player code loaded, and C86E, where the music file is being loaded. It's all defined in Vortex Tracker when you save your song for the ZX Spectrum, so I'm not going to cover this here in detail. You can just install Vortex Tracker and save the song for the ZX Spectrum. It will show you everything, and you can even change those values, but I didn't change them because those are definitely beyond the contented memory, so the music wouldn't slow down. Something like that. Okay, so we've covered the disk operations and the music operations, and now comes the main and the most interesting part, the script interpreter. But before that, we're going to need a method of comparing the strings. And here's a tiny procedure to compare the strings. Basically, to use this, you put the address of the first string in DE and the address of the second string into HL. It loads the character of the first string into A and moves it into B, then loads the character of the second string into A and compares A and B. If the comparison is non-zero, then it means the codes are different. So we return, and the program after which code this can check for non-zero. If we return non-zero, that means we have the strings different. Otherwise, if the comparison is 0, this isn't executed and we get over to here, which compares A to 0, which is a standard for not terminated strings. If both are 0, we return once again, because both strings must have ended. It's not very good idea, because this might actually match when the string matches just the beginning and one of the strings is shorter than the second one, and their beginning matches. And if it's not 0, then just increment both pointers to the both of the strings and go back to the start until we eventually return in here or return in here, whether depending on whether the strings match or not match. Okay, so here's the script interpreter. Yeah, it looks heavy, but yeah, let's just cover it line by line. So, sgrun from start, which basically is used to start from the new script, start from the new scene. It resets the temp flags in here, and now we have an entry point for sgrun from load, which is used for running scripts when we are loading a save file. It doesn't reset the temp flags because we have just loaded them from the save file. Why would we want to reset them? It resets the color of the bottom of the screen to white bright on black background, sets the HL to the script position in the memory. You see it was defined right here, and loads that into the script offset variable. Then the sgrun reads the current position into the memory at which we are currently executing the script, and as this label sgrunning to organize a loop. In the loop we read the current symbol and compare it with D0 hexadecimal. If carry flag is set, that means that the accumulator is lower than D0, so it's not a command, and we go on to sgprintLine, which is a procedure, or more precisely as a program to print the line of the script, which clears the bottom screen, then saves the stack values and prints the current accumulator value, checks the keyboard if symbol shift is pressed, if or if the caps shift is pressed, and if either of them is pressed, it skips over this halt instruction in order to print out the characters in a very fast way, rather than one character per interrupt or 50 characters per second. This allows you to print them even faster by holding the caps shift or sim shift. Then it restores the values from the stack, increments the current character pointer and loads it into the accumulator, and checks if it's 0, because if it's 0 means the line has ended and we don't have anything to print. If it's not 0, then it jumps right here and does everything from the beginning. However, if it is 0, it calls to the SG_wait key procedure, which is right down here. The SG_wait key saves everything to the stack once again, and draws a green enter key icon, and then basically infinitely waits until you press enter using the BFFE port. When you press enter, it just pops everything and returns. Simple as that. So afterwards, it clears the bottom half of the screen, which is used for text output, and falls down to the SGNextChar procedure, which just increments the character pointer, saves it to the variable, and jumps over back all the way to the top. So with this thing, we can already print 0 separated text lines, but not much more than that. In order to avoid passing all the text commands in the scripts, I defined some of the characters that are not used in text to be commands, which are listed over here. So let's look through them. D0 means D0, and 2 bytes afterwards means set the flag at offset of the first byte value to the value of the second byte. So in this area of the flags, this one, it basically writes a value to this area. Simple as that. And let's go ahead and have a look at this. You see, it increments HL to get the flag number, increments HL and gets the value, then saves the current pointer to the character and replaces it with a pointer to the flag area here in main.asm. Then it adds BC, which we loaded with the flag number. So basically, the HL now becomes this place in memory plus the number of flags we skip. Then it writes the accumulator to there and gets back the character pointer from the stack and goes over to the next character. The get game flag is a bit more complicated. How do we jump to definition? Yeah, like this. The get game flag, once again, it gets the next character and sees what flag number this one points to and loads it to BC. Increments HL, gets the value we want and places the pointer to the stack. Then again reads the actual value in the memory into D and compares the value it has loaded into D with the value we wanted that's currently in the accumulator. If it doesn't match, then it goes to the label GF mismatch, which calls to SG advance to else or end if and moves on to the next command. However, if it does match, it increments the HL pointer to the character and checks if we have reached a 0, because a 0 byte means end of conditions. If it's not, it loads the second, it's considered a second flag number, and it moves on, and if everything matches, all the conditions match, it just moves on executing the script. Otherwise, we end up in here, advancing to the next else or end if. Advancing to the next else or end if is done basically by scrolling through the bytes. It saves all the registers because we are going to need some of those. It takes the next byte into the accumulator, checks if it's end if, else, and those are basically the things we are looking for. If we find one of those, we check the variable for the current level counter, because we might have an if inside another if, and we might have those two inside an else block or above the else. Basically, you can have as many nested conditions as you want. So this one just checks B. If it's not 0, then it continues. If it's 0, then it continues execution. Otherwise, it checks if we have end if at least. If it's end if, then decrement the level counter. Otherwise, it's not, so nothing to do. And moves back to here. Also, we can find if temp, or if sys, which are conditions for flags, temporary flags, and system flags, respectively. If we find either of those, we just increment the level counter and move on counting the characters. The level counter is needed exactly to keep track of the nested ifs, because we don't want to jump right off at the nearest end if or else, because that could lead to some unexpected failures. So we'd rather jump off right at the same level as we started. So yeah, something like that. Okay, so next one is set temp flag, which is basically a thing to set the temp flag. Basically, it just, what it does is it loads the current temp flag value into the accumulator and does a binary OR to it. So for example, I can bring this in. If we had temporary flag 1 and 2 set, and the script tells us to set the third flag as well, then it just OR 8. Oh, that's 4th bit, sorry. I'm in hexadecimal, I didn't notice. And that means, you see, this one is set. Then we do AND 4, and we set, oh shit, I mean OR 4, and we set all of them. You see? Simple as that. The temp flags and the sys flags work the same way. Just exactly the same. Just a binary OR operation. The check temp flags or check sys flags are also similar, but they use the AND operation. So basically, like if we have flags 1 and 4 set, and we want to check for the flag 3, we do AND and check for the flag 3. And the result, oh shit, this calculator just drives me crazy. So we have bits 1 and 4 set, and we want to check if the bit 2 is set, we do AND 2. The result is 0, it's not set, so the flag is not present. And let's move on to some other kind of execution. However, if we have it set, then and the second bit will result in the same second bit being set, which means the flag is set. This is how it does it. Basically, it gets the next value, which is the bit mask, to be basically a bit mask of the flags expected to be set, and it gets the system flags for the memory, and it does a binary AND operation, and that checks if the value is the same to the bit mask. If it's the same, that means we have matched and we can move on. Otherwise, we don't take a detour here, and instead go ahead and advance to the next else or end if. We've seen that before. Another command is load file, which basically loads a script file. It loads the DE register pair with the pointer to the script name variable and copies everything it can find in the script until it hits a 00. See, like this. Usually this is 9 characters. 8 characters file name plus 1 character extension in TR-DOS. Something like this. If it finally finds the 00, it goes right here and calls the load procedure from the disk driver. We've seen it before. However, if it doesn't, then it just copies the character, increments the counter, and goes on and on and on. Oops. Should have done that. Okay, the same thing goes for load BGM, except for that it also calls to start BGM routine. Draw screen, same thing. Okay, here comes the next one, interesting one. Game over. What it does is stop the music and set the attributes for the bottom screen to the default of the ZX Spectrum ROM, that is gray background and black text. Then calls to a library called resetfx. I wrote this last year and it imitates the reset of a ZX Spectrum. Then dupe 50 means repeat everything in here 50 times, which should create a delay of about 1 second. Then resetfx input mode, which makes it imitate a basic prompt, another 25 halts, and load the game over string into the HL and call this library again so it imitates as if the user typed this in. And the line that is randomize USR 25,000, pretty much something like as if the user typed that in to reload the game on their own, except for that they aren't doing it on their own. It's all pretty much imitation. Another 50 halts to delay for 1 more second, and restart the script. Copy 9 characters from the start script variable to the script name variable using the LDIR, and call the load routine. We've seen it before in the disk driver once again, and jump to SGROM from start right here, right from the top. So basically returning to the very beginning of the game. I'm sorry, those messages, gotta quit all those messengers and crap. Oh, you shit me? Oh, for God's sake. Okay, another command, E5, means wait a specified number of seconds, which is just the same. Load the bytes into the B register, draw a green timer, return the things from the stack, enable interrupts, and 50 halts is approximately 1 second, so it just uses the DGNZ directive we've seen in the last lesson to wait the specified number of seconds. It just does this all over and over again until the B register is 0 and then jumps on to the next character. Pretty much very simple. Then there are save load commands, which are basically copying the file name into the save file variable and calling the save game or load game routines, and then after loading the game state it also loads the script and jumps to SGROM from load. And the save one just saves and does nothing. Yes, all the saves are controlled by the system script as well, because yeah, it makes it much easier to define different commands for saving. Like you might want to use some kind of a spell in your adventure game to save the game state. So you might not like the default save and load commands. You might want to like lpsi congru to save the current game, something like this. Yeah. Then F2. Oh, how did this F3 this comment is off. This means end if. So F2 is else and else. In the usual use case, the SG advanced procedure we've seen before would skip over the else or end if commands it finds. It would point right after them. However, if we actually stumble upon the else command, that means we were just executing something between if and else. So we don't need to execute anything after the else command. So we'll just advance to the nearest end if, and we're done with it. Something simple as that. And if we stumble upon an end if, it means we are just executing something in the else block or in the if block. And basically we don't give a shit about this command, so we just skip back to the next character and continue executing the script. The F4 directive means stop BGM, and basically just saves the stack just in case and calls the stop BGM procedure. We've seen it before. Nothing else. The clear screen is a bit less straightforward. It saves the stack and calls disappear init, enables interrupts and 7 times calls disappear step and waits for the next screen redraw. That is a library, a tiny piece of code I wrote last year. You can see it by using the link in the description in the fadeout.asm file. It basically creates a colorful fade out effect before clearing the screen, and then it calls the ROM routine to clear the display, because it's too much hassle to write your own screen cleaning routine. We just use the ones from the ROM. I even use the print characters routine from the ROM, and it makes it very simple. Then FD directive is a directive that means a pointer list. A pointer list is basically a list of what the user can type to continue in execution from that pointer. So if we reach FD during an execution, we just gotta skip until we find FE, which means end of the pointer list, because we don't want to print those pointers, we don't want to do anything at all about those pointers. We just want to skip over them, so we just scroll until we find FE, like here. See, if it doesn't match FE, then it goes there. Oops, shit. It does this all over again, this again, until it matches, and then it goes over to execute the next command. Pretty straightforward, I'd say. Directive F7 is end of file, which is used for input search, because if we reach that and we still didn't match any pointer, that means this pointer might as well be not in here at all. So we just stop right there, and that's it. And the FF directive means the user input, means the user should now input their command. It saves everything to the stack and prints a green prompt down below, waits a second to debounce any keys that might have been pressed, I don't know, and prints a underscore to act as a cursor, and prints 08 hexadecimal, which is the left arrow key in the ZX Spectrum terminal notation, so that the next character to be printed would overwrite the underscore. And then it calls the SG keyboard input, which is quite a keyboard driver. It saves the stack and points to the decompressor buffer, because the user might want to enter like 5,000 characters, so we just need to give them the space to do this. Yeah, it's more likely they're going to get out of screen error from the ROM rather than anything in our engine will break. So this loop basically scans the ports for the keys, which I've showed them to you earlier, and jumps to the respective labels, and the respective labels load the respective letters into the accumulator and jump to the key in routine, except for the key 0. Key 0 also checks if the caps shift expressed, because caps shift and 0 means backspace, which is what a shitty way of handling backspace on a keyboard. So yeah, if it detects caps shift, then it goes to backspace. Otherwise, it loads a 0 and jumps to key in, which places the character onto the string buffer, prints it, and prints the cursor once again. Then does a small beeper thing, just clicking like that, and then increments HL, the pointer of the string buffer, and goes back to the input loop right above here. Yeah, to check if the key is set, I'm using the carry flag. Basically, I read from this and I get those 4 bits into the accumulator. How do I check? Well, I could do an AND with different masks all the time, but this is slow, this is too monstrous construction. So let's just do it like this. We rotate the accumulator to the right. That means we shift all the bits to the right of the accumulator, and whatever didn't fit ends up in the carry bit. And then we can check the carry bit if the first bit of the accumulator, well, what was formerly the first bit of the accumulator, if it was 0 or not. And after rotating to the right, if the carry flag is not set, then this means this key was pressed. Otherwise, it means this key wasn't pressed. Simple as that. And the enter handler basically adds a 0 to the end of the string we are inputting, hides the cursor, and goes to the end input. The backspace is a little more complicated. It checks if we are already at the beginning. Otherwise, it just goes over to here because it can. Whoops, I think I found an error in here. I didn't actually check if it does work, but oh no, it's all fine. Looks like it's all fine, yeah. It's not an error, it will jump out of here because we saved those 2 here and we saved those 2 before pressing the key, you know? Yeah, you should really balance the stack calls. You have to keep track of what you're pushing and what you're popping, because if you push more than you pop, then you might end up popping something unexpected or overflowing the memory area allocated for the stack, breaking everything, the load ends and all that kind of stuff. And if we can backspace, decrement the current buffer pointer, load a 0, meaning end of string, to that new position, and hide the cursor, move left twice, print the cursor over the character we've just erased, and move back once again so as to erase the cursor when we print something, and do a click through the beeper once again, and then goes back to in loop, something like that. After the user has finished their input, let me find this again, user input, go to definition, okay. So after the user has finished their input, the decompression buffer now has the string they have inputted ending with a 0 and some trash from previous files or previous inputs or whatever. So we're going to store the current pointer of the string and load the script beginning of the system script, not the main script but the system script, into HL, find the next start of the pointers, and once we find the start of the pointers, which is FT, it compares every single line, every single pointer terminated with a 0. Using that routine, it compares every single one of them to what the user has inputted. If it matches, it goes to find the end of the pointer list like we did above, and if it doesn't, it just goes ahead and ahead until the end of the pointer block. If nothing is found, it goes on and on and on and on until it eventually either finds something or reaches F7, which is end of file. If it reaches end of file, it goes to EOF, and EOF means print the character, the line at the end, which is bad command of file name, just the same DJ and Z type routine we've seen in the previous lesson. So yeah, that's the whole engine. Yeah, there are also some calls to the ROM routines, but they are mostly non-complicated and boring crap. So yeah, that's the whole engine. It's very simple, contrary to what many people might say that, oh wow, it's such a big engine, you have ported such a big game. It's nothing special actually, it's just the compiler that compiles the text files to that script. Let me find this. Okay, code and script to zx.py. That is what makes everything possible. It basically reads a text script file, which looks something like this. You see, it's a text script. Oh, I just spoiled you some Easter eggs of the game, yeah. And it processes it into the same binary files. It's not a Python lesson, so I'm not covering this. It's pretty simple, you can find it in the link down in the description. It's called script to zx.py in the main repo, and you can see how it works just by reading the code. It's not that something much, not something very special. So yeah, I hope this was interesting and helpful. You can play the game by downloading the disk images of the same repo, but remember you have to have purchased a copy of the original novel beforehand, otherwise it's not legal for you to play it. So I hope this was helpful for you and interesting to look into how a visual novel or text adventure game would work on a ZX Spectrum. I hope that was understandable, so send me your questions in the comments if you didn't get something. Yep, and hopefully see you somewhere sooner than the next 4 years. Bye bye!